Okay. Hi, it's Theo, and this is the block slope problem. Okay, so here's the situation. We have a mass of mass m, and it is on this slope, which is at an angle theta to the ground. And there's also a sensor somewhere along the slope, and the distance parallel to the slope from the mass to the sensor, or actually from this point is also the ground. From the ground to the sensor is d. And then finally, the mass is projected upwards along the slope with an initial velocity to v0, or v0. Okay, so first we are asked to find the acceleration of the block. So for this, and it's saying a given acceleration at time t. For this, I actually don't think I'm going to need t because acceleration will be constant. So I'm going to use force equations. So let me just draw a little free body diagram for the mass. Okay, so we've got gravity as always, going straight down. And we've got a normal force kind of going outward from the slope. And I'm also going to kind of draw theta there. Okay, so because our axes, they've actually defined the axes for us because they're relative to the sensor. Because our axes are kind of matching up with the normal force, I've got to project gravity onto those axes. So let me make this a little bigger. So here's mg. So let's kind of project it. Alright, so if this is theta, that means this angle is 90 minus theta. So this angle is theta. Okay. So I'm finding the acceleration. I know that the mass is not going to be going off the ramp. In other words, its y position is not going to be changing. So I'm just going to look for the acceleration and the force in the x direction. So in the x direction, in other words, this component is going to be mg sine theta. So here's my sum of forces. And normal force does not factor in because it is perpendicular to the x-axis. So the only force is going to be mg sine theta, and it's going to be a positive force because it is pulling the block down the slope, which in this case is in the positive x direction. Okay, and that equals mass times acceleration. So therefore, acceleration is g sine theta. Okay, that is part A, part I. Okay, so next we are finding, we're finding the velocity. Okay, so in this step I'm going to use kinematics equations, but I'm also going to rely on this that I found last time. So one of our kinematics equations states that the velocity at a given point is equal to the initial velocity plus the acceleration times the given time, assuming the acceleration is constant, which in this case it is, as forces here are not changing. Okay, so we're given initial velocity, so that's good to go. Oh, one thing. Actually, it's important to note this is an initial speed. So the v0 that it gives us is an initial speed, but you'll notice this is actually in the negative x direction. So because we're talking about x velocity, this is going to have to be a negative v0. Also, I'm only talking about x velocity again because this block is not moving in the y direction, so I don't have to consider y components at all. Okay, so from there we just plug in acceleration, and we get negative v0 plus gt sine theta, and there it is. That is our velocity. Okay, so next we are asked to find the position for the block at a given time. So for this I'll use a different kinematic equation. Alright, so this equation may be the most common of the kinematic equations. One thing though, again, v0 is going in the negative x direction, so this gets changed to a negative. And then also our initial x position, based on these axes is equal to capital D. And then here we just plug that back in. Acceleration is g sine theta. So that is d minus v naught t plus 1/2 g t squared sine theta. Okay, there we go. So now we have acceleration, velocity, and position. Okay, so next we are asked to find the minimum x position of this mass. In other words, kind of when it goes up, it'll eventually reach a point where the acceleration going this way will make the velocity start to go this way as well, and it'll start going back down the ramp, and at that point, kind of right where it starts to go back down, or where it stops going up, it'll be the minimum distance from the sensor. In other words, at that point, the velocity will be 0. So, we can use a kinematic equation here. We know that we're kind of using this equation, right? So, we know that 0 equals negative v0 plus acceleration. I'm solving for. Oh, wait, I'm solving for the minimum x. Yeah, that's fine. Plus acceleration times time. And then I'll just plug in my acceleration, which is g sine theta. And now I'm just going to solve this for time. And then once I get time, I'm going to plug it back in to this equation and see if I can find x. Okay, so in this case, time equals v naught over g sine theta. Okay, just algebra. And then I'll just plug that back in. So we've got x min equals, x naught again is d. And I'm actually just kind of going to use this equation. So minus v naught time. All right, so time is v naught over g sine theta. So I'll just plug that in. So minus v naught squared over g sine theta. And then plus 1/2. So now we have a v naught squared over g squared sine squared theta times a 1/2 and times a g sine theta. So that g sine theta will cancel out one of the g sine thetas. So that'll give us 1/2. Okay, and these are like terms. So we have d minus okay, so there we go. That is the sort of minimum x position that the mass ever reaches. Okay, so let me just find the next problem. Okay, we are asked to graph the position, velocity, and acceleration of the block over time for these axes. Okay. Here's my position graph. The block is not going to start at 0 because relative to the sensor, when time equals 0, the block starts at a distance d. So we'll start at d, and then we know that at the end, I'll just kind of label this like t final. At the end, it goes all the way back down to the bottom of the ramp, so it will reach d again. Okay, great. So, based on this equation, this is a quadratic equation, right? So that will form a parabola, and we can tell it's kind of a upwards facing parabola because this constant here is positive. So it's going to look like this. And one important thing, it's not going all the way to 0, and that is because the mass does not necessarily make it all the way to the sensor. It actually makes it all the way to an arbitrarily small number, which we already defined. It is x min. So there we go. And for x min, you can just refer down to this equation. All right, so that is our x graph. Move over here. Okay, so now we'll do our velocity. Oh, I guess, well, whatever. Okay. Okay, so in the beginning, our velocity is pointing this way, so that is negative. And it's actually giving us that velocity, or it's giving us it as a speed, but in this case it is negative initial velocity. And then at the end, because at this point in the problem we have conservation of energy, we're going to end up with the same velocity, well, the same speed, but it will be positive. So at the end we'll end up with positive v0. And if we look at our equation for velocity, this is linear with respect to time. So it's also increasing because g sine theta is positive. So I'll label this final time, and we'll kind of go through there. That's not a great drawing, but we'll go through there. Just a note, so here, when the velocity is 0, that's kind of when it reaches its peak, and that's the same as when it's at x min. So I'm going to label this minimum time, just to clarify that these times are the same. Okay, and then finally, okay, we got acceleration. So based on this equation, assuming our ramp is not like falling and we're not like going to a different planet, or the ramp is not massive and our height is actually changing, g sine theta is constant. So our acceleration is also constant. It is also a positive number. So yeah, pretty simple acceleration graph. And there we go. That's our 3 graphs. So that's part C. But this is part B. That's part C. Okay. Now we're asked to, so after the block reaches the ground, it is going to slide along the ground, but, let's see, yeah, so the ground has friction, and it's giving us a frictional constant, mu k. So I'll just kind of draw a free body diagram of the mass on the ground. In this problem, the friction only acts on the block once it has reached the ground. So and the friction is going to act opposite to the velocity, which is going to be in this direction. Okay, so for this problem, I'm going to redefine my axes because these aren't very convenient. So here's my new x and y axes. Okay, so I'll do sum of force equations to find the normal force, and I'm going to use that to find the force of friction. Yeah. Okay. So in the y direction, we have one positive force, which is normal force to the ground, and one negative force, which is gravity. And the block is not levitating off the ground or falling into it, so the acceleration in the y direction is 0. Therefore, mass times acceleration is 0. Therefore, normal force equals mg. Okay, and we know that friction is equal to mu kn. So now we've got it. So it's mu k mg. Okay, we've got friction. So now we're basically asked to find the distance the block slides along the ground before it reaches a stop. So in this case, I'm going to use energy equations, because that way I kind of get to use my friction conveniently. Alright, so at the beginning, also our y position, this kind of y position, is not changing. So I'm going to forget gravitational potential energy, because it is constant and it'll be the same on both sides, so I can ignore it. Alright, so on the left side, I'm going to put a v naught squared here. The reason I'm putting v naught is that consider the first situation again, then there's no friction when it's on the ramp. So, because of conservation of energy, its speed at the beginning of the ramp will be equal to its speed at the end, which is v naught. So that's why I'm not allowed to use v naught here. So that's all the energy at the beginning. At the end, it is no longer moving with a velocity, so there's no kinetic energy. And the energy loss is due to friction, so that goes here. And I'll just kind of substitute that in. Oh, whoops. And there's one more thing, distance. So the work loss due to friction is equal to the force of friction times the distance traveled. So that's great because that's what it's asking for, distance. So now I can just solve this. Okay, we get v naught squared over 2 constant of kinetic friction, gravitational constant. Okay, can you read the final problem real quick? Yeah. Okay, so now ignore everything that just happened. Suppose instead of the ground having friction, the ramp has friction. So kind of the first part of the scenario. Again, the mass travels up the ramp and then back down, but now the mass has friction with the ramp. We're not asked to calculate anything here, we're just asked to graph the velocity again. Okay, so again, the starting position is the same. We're starting with a velocity of negative speed. All right, and also on the kind of like, it labels something for us. Oh yeah, let me make this graph a little bit bigger actually. So it's labeling our final time, and this is kind of interesting, half our final time. So the time is halfway down. All right, so let's think about this. So when the block is going up the ramp, on these axes, when it's going up the ramp, the friction is pointed down the ramp, which points the friction in the positive x direction. So that will help, kind of besides, if you take this slope, the friction is actually going to increase this slope because it is moving with the acceleration, and so it will increase the velocity more. So I know that kind of before it reaches the top, when it's moving up, the slope of the velocity will be increased. I'm not going to draw anything yet, but I'm keeping that in mind. All right, so when the mass is moving down the ramp, the friction is now in the opposite direction. It's moving up, so that is moving opposite the acceleration, and that is going to decrease the slope of the velocity. So I know that kind of for the first half of my motion, the slope is going to be increased, and the slope is going to be decreased. But it still reaches the bottom of the ramp. And if we kind of think about energy equations, we could consider force loss due to, energy loss due to friction, but that's equal to force times distance, and at the bottom, distance is 0, so therefore velocity will be conserved at the end. So it still must reach v naught at the end. But this slope must be greater and this slope must be less, and the only way for that to be possible is if kind of the x-intercept here is before half the time is over. There's no way to draw it such that this slope would be greater and it intersects after the first half of the time. Okay, so, and then here's the time where we reach our minimum position. This is of course different from this time minimum because it's a different situation, there's now friction, but yeah, that is our graph. Okay, so just to sum things up, we've got our acceleration, g sine theta, always positive. We've got our velocity, which can be negative or positive, and it is linear, so negative v naught plus gt sine theta. We've got our x, which is actually quadratic, and it's distance minus v naught t plus 1/2 gt squared sine theta. Again, we got all of those using kinematics. And then we solve for the minimum x position there is, using those same kinematic equations, which is this. Then we graphed position, velocity, and acceleration relative to time. Position is quadratic, velocity is linear, and acceleration is constant. That makes sense because velocity is the derivative of position. So if you think of this as an x squared term, it'll become an x term. Then take the derivative again to get acceleration. That x term becomes a constant. So there you go. So then we took a look at the block sliding along the ground with friction and used force equations and energy equations to solve for the distance it travels before it reaches a stop, which is v naught squared over 2 mu kg. And then finally, we considered friction between the block and the ramp and just graphed that velocity again, taking the friction into consideration. So yeah, thanks for watching.